If I have an electric field going off to the right, and let's just go ahead and establish our convention here. So I hat to the right, J hat up or towards the top of the page, and then K therefore becoming out of the page in a right-handed coordinate system. So I have some uniform electric field going off to the right. And in that I have a dipole. And as established earlier, it would rotate about some central point right here. I have a force acting in this direction, and I call that F plus, and I have F minus acting in that direction. The distance between them is S, and the electric dipole moment P, the vector, is if going from negative to positive in that direction, and the magnitude of that is Q times S. And that is the magnitude. So I have some angle theta here. And what I want to figure out is what is the potential energy stored in a dipole in an electric field. What I want to imagine is that it starts out at some initial angle theta, some theta initial, and it's rotating this way. Now, since the torque is in the opposite direction, the torque will cause it to slow down, since torque and angular displacement are opposite each other. Or more, we can also word it as since the torque and the angular velocity are in opposite directions. So it will be slowing down as it's moving this way. That I know that the conservative work is equal to the negative change in potential energy. This is one of the work-energy relationships that from the first semester course. And work is equal to the conservative force dot displacement. However, we're dealing with rotational motion here, and so using x and force do not seem to make a lot of sense. And so we have to put in the rotational analog of it. So this is torque, the conservative torque dot d theta, from some initial angle to some final angle. So that's theta I here, and then that would be theta F. Now I know that the torque is in the negative k direction, but the change in the angle is in the positive k direction. And so the dot product between these two, they are 180 degrees opposite each other. So that will give us a negative theta initial, theta final, torque, the conservative torque times d theta. And that's equal to the negative of u final minus u initial, or negative u final plus u initial. Now torque from a previous video is equal to, in this situation, the P cross E, or the magnitude of the torque is going to be PE times the sine of theta. And so this is equal to negative integral from theta initial to theta final of PE sine theta d theta. And the dipole moment, the electric dipole moment, is just Q times S. It's a positive number. The magnitude of the electric dipole moment is a constant. The electric field is a constant, thus the term uniform. So those are going to get pulled out. So I get negative PE times the integral of sine theta d theta, from some initial theta to some final theta. Integral of sine theta d theta is negative cosine, so that negative will cancel out with that. And so what I'm left with is PE cosine theta, from some theta initial to theta final. And then plugging in, go to the new piece of paper here. So what we have is our work is PE cosine theta final minus PE cosine theta initial. And that is equal to negative UF plus U initial. So this would make sense. I could make this work if I just assign that the potential energy is equal to negative PE cosine theta. PE cosine theta that's just the dot product. If you recall, if I have P going in this direction and if I have E going in that direction, the dot product multiplies parallel components. So if that angle is theta there, this length right here would be P cosine theta. This would be P sine theta. So for dot product, I'm multiplying this times the magnitude of the electric field. So that's PE cosine theta. So that is just negative P dot E. You do E dot P also, the commutative property holds for dot products. Also note that all I really did on this derivation here was to derive, if I multiply it through by a negative sign, I would have that the change in potential energy is negative PE cosine theta final plus PE cosine theta initial. That's the change in potential energy. And so I can always tack on a constant here. In essence, I can make zero anywhere I want it to be. Traditionally, zero happens when the electric dipole moment is perpendicular to the electric field, but it doesn't have to be. But that's the formula for the energy stored within a dipole. And don't forget, for every, there's all sorts of different potential energy formulas, and this is just yet one more.